Good afternoon, students. In previous class, we discussed about how we are going to convert this finite automata to regular expression. In today's class, we are going to discuss what are the various types of applications of regular expressions. Applications of regular expressions means where we are going to use these regular expressions. What is the use of these regular expressions? Here, generally, basically, the regular expressions are used for construction of searching tools. Here, by using this regular expression, we can construct the searching tools. Here, various types of searching tools are there. Generally, for example, here EGREPA1 searching tool is there, which is going to be used in Unix operating system. Here, this particular tool is going to use to search for a text file, whether the text file is present in the database or not. We are going to search for this tool. Here, basically, these regular expressions are used for the searching to construct a searching tool. Next, here generally we are going to use various types of patterns. Depending upon the patterns, we are going to search whether the file is present or not, whether the text file is present or not, whether any pattern is present or not. Depending upon the patterns also, we can construct our searching tools by using the regular expression. This is the basic use of regular expressions. Here, while we are going to convert, while we are going to use any regular expression, that particular regular expression must use some of the properties. Here, generally, here algebraic laws of the regular expressions are there. Here, by using this algebraic laws, we are going to check whether the given language is regular or not. We are going to check whether the given language is regular or not. By using these laws, algebraic laws are there, closure properties are there. Here, by using these properties, we are going to check whether the any finite automata is a regular. By using this finite automata, we are going to construct any regular expression or not, or else whether the language is empty or not. All those things we are going to check by using this regular expressions. Here, to check all these things, we are going to use some set of rules are there. Here, for example, here we are going to discuss about algebraic laws of regular expression. Here, there are 5 algebraic laws are there. First one is the associativity and computativity. Here, in this case, L plus M. L is one language. Here, for example, union of two language. L is one language, M is one language. If L plus M, union of two languages, equivalent of M plus L. L plus M is equivalent of M plus L. This is the general thing. L plus M is equivalent of M plus L. Union is also the regular. If L comma L are, if L and M two are regular languages, then L plus M is equivalent of M plus N. Right. Next one is the associative law. What is associative law? If L, M, N, 3 languages are there. If L, M, N, 3 languages are there, then L plus M, first we have to perform L plus M, union of these two. Then we have to perform, then union of L plus M plus N. Here it is equivalent of, first we have to find the union of M comma N, then we have to find the union with L, M plus N. This is the associative law. Next one is the here for the concatenation, associative law for union. This is the associative law for union. Next one is the associative law for concatenation, LM-N. So, first we have to perform the concatenation of L comma M language, then we have to perform concatenation of LM and N, and it is equivalent of, first we have to perform the concatenation of Mn, then we have to perform concatenation of L and Mn, right. Here concatenation is not computative. Here Lm is not equivalent of Ml, Lm is not equivalent of Ml. If L comma L both are regular languages, then Lm is not equals to Ml. L plus M, union is we can perform the union operation on two languages L comma M, whereas we can't perform the concatenation of two languages. Lm is not equivalent of Ml, right. Next law is identities. Here you see here pi, epsilon, these are there. Here pi, epsilon is there. Here generally pi plus L. Here these are the identity laws. Here I1, I2, I3, I13 laws are there. In that case also epsilon is there, pi is there. Pi plus L. Here generally here pi is different and epsilon is different, right. Here if pi is there, what is the regular expression for this one? Here pi. here epsilon is there, here for the pi regular expression is different, for epsilon regular expression is different. So, pi and epsilon both are different. Pi is here, pi plus L equals to L plus L plus pi equals to L, and epsilon into L comma epsilon equal, it is equivalent of L. Yeah, identity for concatenation, identity for union. Here pi L equivalent, it is equivalent of L pi, it is equivalent of pi, pi is the concatenation. Here these are the identity laws of any language if L is a regular language. Next one is the distributive law. Distributive law, see here. Here this is the association, L plus M plus N is there. Here concatenation and union both we can perform here. L concatenation of M plus N, it is equivalent of L M plus L N. M plus N into L is equivalent of M L plus N L. Here one condition is there. In this case we are having L M N, 3 should be the regular language. These 3 should be the regular expressions, right. Item pendant law. Here L plus L equivalent of L. Here generally L plus L. Whenever we are going, one language is there, again we have to use the same language, then it is equivalent of L plus L, it is equivalent of L only. Here closure properties are there. L star whole star is it is equivalent of L star, pi star is equivalent of epsilon, epsilon star equals to equivalent of epsilon L plus. Here positive closure is there, negative closure is there. Here positive closure, L plus is equivalent of L plus L plus L concatenation of L. L star is, it is equivalent of, here empty symbol is there, pi symbol is there, epsilon symbol is there, epsilon plus L plus LL is there. Here we can write the connection in between L plus and L star. L star it is equivalent of L plus epsilon, then we can get L star, closure of L, closure of L. These 5 are the algebraic laws of regular expression. These 5 are the algebraic laws of the regular expression. Next one is the properties of the regular expression. Here generally there are 2 types of properties are there. First one is the closure properties on regular languages, and the decision properties of regular languages are there. Here we are going to divide the properties of the regular languages in 2 cases. First one is the closure properties, second one is the decision properties. Here generally here now we will go for the closure properties on regular languages. Yeah, closure property means if any language is closure, closure, then what type of operations we can perform on that particular language, again that is going to be satisfied the closure property. Here closure properties on regular languages are defined as the certain operations on the regular language which are guaranteed to produce the regular language. Whenever we are going to perform any operations on that particular language, again still that particular language is going to be regular language only, right. Closure refers to some operations on the language resulting in new language that is of some same type as originally operated, that is regular. Here before performing any closure operations, here if that particular language is regular, what type of operations we can perform on that particular language, again that particular language is regular, whether union, concatenation, closure, whatever it may be, that particular language is remaining same as regular only. If any language is not regular, non-regular language is there, if we are going to perform the closure property, then that particular language is non-regular only, right. Here generally here regular languages are closed under the following operation. First one is the keen closure. For example, L and M are 2 regular languages. Here L comma M are 2 regular languages. Now keen closure property is there. In keen closure property, here L is a regular expression whose language is L. Here for example, R is a regular expression whose language is L. For example, I am going to define one language is there, that particular language is going to be defined, by the L. R is a regular expression. Here that particular regular expression belongs to the language L. Then R star is a regular expression whose language is L star. Here R star, closure of R means R star. If R star is regular expression, then that particular language is L star is there, right. Positive closure means if R is a regular expression whose language is L, then R plus is a regular expression whose language is L plus. Here positive closure means there is no epsilon, is there in the positive closure. Key enclosure means R star. If R is a regular language, that particular language is going to be set in the language L. Then if R star is a closure, R star is a regular expression, then the language of that particular regular expression is L star. If R is a regular expression of L, then positive closure of that particular regular expression is R plus, then that particular regular expression is going to present in L plus only. So, this first one is the key enclosure, second one is the positive closure. These are the closure properties. Third closure property is union. Third closure property is union. Here for example, if L1 and L2 are two regular languages, if L1 and L2 are two regular languages, then L1 union L2 is a regular. If L1 and L2 are two regular languages, then L1 union L2 is also the regular language. Here proof is there, no need to read this proof, just you have to by heart what is the closure properties of the regular languages, right. Yeah, properties of the regular languages means you have to read this one, closure properties and decision properties, you have to write the closure properties and decision properties. In closure properties, first one is the key enclosure, second one is the positive closure, third one is the union. Here union means if L1 and L2 are two regular languages, then L1 union L2 is also the regular language. Next, fourth one is the concatenation. If L1 and L2 are the regular languages, then L1 L2 is regular. Here we are not going to write L1 intersection L2. Here we are not going to write L1 intersection L2. Concatenation means L1 L2 only. Here we are not going to write L1, sorry, we are not going to write L1 intersection L2. L1 intersection L2. We are not going to write like this one. Here L1 L2 is the concatenation. L1 L2 is also the regular. If L1 and L2 are two regular languages. For example, if L1 is a regular language and L2 is a non-regular language, in that particular case L1 L2 is not a regular language. L1 L2 is not a regular language. Here when we are going to say the regular L1 L2 is a regular language, if L1 and L2 both are regular, if L1 and L2 both are regular, then only we are going to say that L1 L2 is a regular language. Third one is the star closure. Here if L is a regular language, if L is a regular language, L star is a regular language, then L star is regular. If L is a regular, then L star is a regular. Here star closure, key enclosure both are same. Star closure and key enclosure both are same. Next one is the complement. L is a regular language, then L bar is also regular. L bar is also regular. See here L bar, here epsilon star, here sigma star minus L. L bar is going to represent the sigma star minus L. It is equivalent of sigma star minus L is also regular. Next one is intersection. If L1 and L2 are regular, then L1 intersection L2 both are regular. Intersection and concatenation both are different. If L1 and L2 are both are the regular languages, then L1 L2 is regular. If L1 and L2 are regular languages, then L1 intersection L2 is also the regular language. L1 and L2 is also the regular language. Here in this case, see here L1 intersection L2 is L1 union L2. Here no need to go for the proof, just you have to remember the what are the various types of closure properties of regular language. Next one is the set difference is there. If L1 and L2 are the regular languages, then L1 minus L2 is also regular. If L1 and L2 are the regular languages, then L1 minus L2 is also the regular language, right. Next one, the reversal. Reversal means here reverse of the given string. If for example, let W equals to A1, A2, A3 up to AN be a string, then reverse of the W means AN minus 1. See here, we have to start from AN. So AN, then followed by AN minus 1, AN minus 2, AN minus 3 up to A1. Reverse of the W, AN minus 1, AN minus 2 up to A1. For a regular language, L subset R equals to sigma star, then reverse is W belongs to sigma star, reverse of W belongs to L. If L is a regular, then reverse of L is also the regular language. If reverse of the L is also the regular language, so, right. Here, these are the various types of, here these are the properties of the regular languages. Next one is the homomorphism. Here in this case, let us sigma and be a two alphabets, then the function is called homomorphism. Let W be the string, W belongs to sigma star and W equals to A1, A2 up to A, then homo h of W equals to h of A1, h of A2 up to h of AN. Generally h is going to represent in terms of A1, A2, A3, A4 up to AN. Then h of W, how we are going to represent h of W? H of W is equivalent of h of A1, h of A2, h of A3 up to h of AN. If L is a regular language, then h of L, homomorphism of L is also regular. Homomorphism of L is also regular. Inverse of homomorphism is also regular. Ninth one is the inverse homomorphism. In this case, here if L is a regular, then H inverse L is also regular. These are the 9 properties of, these are the 9 closure properties of the regular languages. Here properties of the regular, generally I repeat, closure properties of the regular languages are going to divide it into 2 parts. First one the closure properties, second one is the decision properties. In closure properties, key enclosure is there, positive closure is there, union, concatenation, star, complement, intersection, here set difference, reversal, homomorphism, inverse homomorphism, all those are the properties of the regular languages. Now go for the second one, decision properties. Here what do you mean by decision properties? The closure properties, already you know the closure properties. Now second one is the decision properties. In decision property for a class of a language is an algorithm that takes a formal description of a language. For example, description of a language, how you are going to describe the language? By using the DFA, by using the NFA, by using the Turing machines, by using the push down automata, you are going to describe the particular language. You do not know what do you mean by push down automata and Turing machine, all those things. Just up to here you learn that DFA only, that is the reason here I am going to write this DFA. Then it tells whether there are not some property holes. Here in decision properties, you are going to check whether the language L is empty or not, whether the language L is empty or not, we are going to check, right. Here if any language L is empty, if any language L is empty, we are going to check by using the various types of properties. We are going to check whether the language is empty or not, whether the language is empty or not, we are going to check, right. Here by using, here see here by using these properties, by using the closure properties, we are not going to check whether the language is regular or not. Here in this case, by using the decision properties, we are checking whether the language is empty or not, or else whether the language is finite or not, or whether the language is non-empty. Here we are checking by using the decision properties, we are checking for that particular language whether that particular language is going to satisfy some set of properties or not. Here when we talk about the protocol represented as DFS, we noted that the important properties of a good protocol were related to the language of the DFA, right. Here we are going to check by using the decision properties, we are going to check whether the language L is empty or not, whether the language is finite or not, whether the language is non-empty or not, or else whether two languages are same or not. How you are going to recognize two languages are same or not? If the same languages are going to be accepted by the same finite automata, then we are going to recognize that particular language, those two languages are same, those two languages are equivalent, right. By here we are having the various types of DFAs, NFAs are there. By using those DFAs and NFAs, we are going to check whether the language are same or not. Here by using the decision properties too, we are going to check whether these two languages are same or not, these two languages are same or not. How you are going to decide? By using the minimization of the DFA, or by using the equalization of DFAs, we are going to check whether the two languages are same or not. Here that is, if two DFAs define the same language, then we can say that the two languages are equivalent. Here by using this, here at the end we are going to decide that by using the decision properties, we are going to check for that particular language whether the language is empty, whether the language is not empty, whether the language is accepted or not, whether the language is regular or not, all those properties, decision properties are going to check by these decision properties of the regular languages. Generally there are 5 decision properties of, generally there are 5 decision properties are there. First one is the emptiness, second one is the non-emptiness, third one is the finiteness, fourth one is the infiniteness, fifth one is the membership, sixth one is the equality. Yeah, these are the 6 decision properties are there. By using these 6 decision properties, we are going to check whether the languages are regular or not. Here, first one is the first one, emptiness and non-emptiness. Here I combine these 2 properties, emptiness and non-emptiness. What do you mean by emptiness? Here select the state that can't be reached from the initial state and then delete that particular state, means that is the unreachable state. Here in step 2, here with here to check emptiness and non-emptiness of the regular languages, first you have to select any state, select the state that can't be reached from the initial state. Select the state that can't be reached from the initial state means, here if from the initial state if you are not going to reach any state means that is the unreachable state. So we can delete those type of unreachable state, we can delete those type of unreachable state, right. Second step is, if the resulting machine is consisting of at least one final state, then the finite automata accept the non-empty language. Yeah, if the resulting machine, if whenever we are going by using the regular expression, if we are going to construct any, finite automata, then that particular resultant machine is going to be used by this one. If the resulting machine is consisting of at least one final state, then the finite automata accept the non-empty language, then the finite automata is going to accept the non-empty language. Third one is the step 3, if the resulting machine is free from the final state, then the finite automata accept the empty string. If the resulting machine is free from the final state, then the finite automata accept the empty language, then the finite automata accepts the empty language, right. Next one is here, next one is finiteness and infiniteness. The next property is finiteness and infiniteness. Infiniteness and infiniteness of a regular language is going to be decided by using this property. Here in this case, first we have to select the state that can't be reached from the initial state, then we have to delete such states. It means that unreachable state, we have to delete such states, right. Here in step 1, first we have to select the state that can't be reached from the initial state. It means that those states are unreachable state. So we have to delete such type of unreachable states in first case. In second step, here select the state from which we can't reach the final state. Here in some cases, here we can reach from the initial state to that particular state, but by using those states we can't reach the final state. In that particular case, we are going to deleting such type of states. Now it means that this type of states are known as the dead states. This type of states are known as the dead states. So we have to delete such type of dead states. Third one is, if the resulting third step is, if the resulting machine consists of loops or cycles, then the finite automata accepts infinite language. Here first we have to remove the unreachable state, then we have to remove the dead states. After deleting the unreachable state and the infinite state, we have to if the at that time, if that resulting machine is consisting of any loops, then we are going to set that here that particular finite automata is going to be accept the infinite language. That particular finite automata is going to accept the infinite language. Next step 4 is, if the resulting machine doesn't contain any loop or cycles, then the finite automata accepts only finite language. Here, if the resulting machine doesn't contain any loop or cycles, then the finite automata accepts only infinite language. Then the finite automata accepts only infinite language, right. Now, here for finiteness and infiniteness is complete. Next one is the membership property. Here membership property means, here generally it is in membership property, we are going to verify an arbitrary string is accepted by the finite automata or not. Then if that particular string is going to be accepted, then it is a member of that particular language. It means that if any language is going to be accepted, if the string is accepted means that particular language is going to be accepted by that particular finite automata. Or if any string is not accepted, if any string is not accepted by the finite automata, it means that that particular string, that particular language is not going to be accepted by that particular finite automata. This is known as the membership. For example, let M is a finite automata that accepts some strings over an alphabet, and let W be any string defined over the same alphabet. Then if there exists a transaction path in M which starts an initial state and ends in any one of the final state, then the string W is a member of M, otherwise W is not a member of M, right. Here it means that if the string is accepted by the finite automata, how you are going to recognize that particular string is accepted by the finite automata? Whenever we are going to process that particular string on the finite automata, if we are going to reach the final state, if you are going to reach the final state, then that particular string is accepted. If you are not going to reach the final state, then that particular string is not accepted by the finite automata. Membership means we are checking whether that particular string is accepted or not. If the string is accepted, then that particular string is, then the string which is having that particular language is accepted by the finite automata. This is known as the membership. Next one is the equality. Equality means we are going to check whether two finite automata M1 and M2 are said to be equal or not. Here, how we are going to check these two are equal or not? If the same set of string is going to be accepted by M1 and M2, then M1 and M2 both are equal. Here it means that same set of strings means same set of languages. Here string language means languages consisting of string. Languages consisting of string. If the string is accepted means that particular language is going to be accepted. That particular language is going to be accepted. If the two machines, if the two finite automata M1 and M2 are both are going to be accepting the same set of string, same set of languages, then those two finite automata are equivalent. Then those two finite automata are equivalent. Or minimize the finite automata and minimal DFA will be the unique. Whenever we are going to minimize those finite automata, then we are going to get only unique finite automata. Then we are going to deciding that M1 and M2 both are equal. These are the closure decision properties of the regular languages. First one is the emptiness, second one is the non-emptiness, finiteness, infiniteness, membership and equality. These 6 are the decision properties of the regular languages. With this, decision properties of the regular languages is completed. Generally properties of the regular, I repeat, properties of the regular languages are going to divided into two parts. First one is the closure properties of the regular language, decision properties of the regular language, right. With this, properties of the regular language is completed. Next, move on to next topic, that is the pumping lemma. Very important topic, pumping lemma. Here pumping lemma means, here by using this pumping lemma, we are going to check whether the given language is regular or not. Basically, why we are going to use this pumping lemma means whether that particular language is a regular or not. We are going to check whether the language is regular or not. Here this pumping lemma is one theorem. By using this particular theorem, we are checking that whether the given language is regular or not. Now here theorem for pumping lemma is, if L is a regular language, then there exists a constant n. Here you have to remember this theorem, right. If L is a regular language, then there exists a constant n, where we are going to take this n as a constant value. Here generally this n is depends upon the L value, such that for every string W in L, such that always mod of W, length of W is greater than or equals to n. Mod of W is greater than or equals to n, that is length of W is always greater than or equals to n. Then we can break W into 3 strings, W equals to x, y, z. If here we are going to take the w in terms of three strings w equals to x comma y comma z, w equals to x y z. Here in this case y is always greater than 0 and y is not equivalent to epsilon, x y is always n less than or equals to n. See here, this is n is the constant is there, so it is always less than or equals to n. For all k greater than 0, this string x y power k z is also in L. Here it should follow these three properties, it should follow these three properties, then only we are going to deciding that particular language is a regular language by using pumping lemma. Here whenever you are going to checking any language is a regular language or not, by using this pumping lemma we have to follow this theorem. Here we have to take one constant value n, we have to take one string w, that particular string must belongs to L and that particular string is going to represent in terms of three strings w equals to x y z, always y should be greater than 0 and y is not equivalent to epsilon. Next one is the x y always less than or equals to n, this is the property of the pumping lemma, theorem of pumping lemma. Here we are not going to check anything, x y less than or equals to n. Next one third is for all k greater than or equals to 0, this string is x y power k z is also in L. Yeah, this is the theorem for pumping lemma. By using this theorem we are going to check whether the given language is regular or not. Here these three properties we are not going to change these three property. Why? Because for example 2 plus 3 equivalent is 5, 2 plus 3 is equivalent of 5. It means that why we are going to take this 5 instead of 5 we can take 6, right? No, we can't take 6. Why? Because 2 plus 3 it is same. 2 plus 3 whenever we are going to perform any operation plus operation we are going to get 5 only. In the same way this is the theorem, you have to remember this theorem. By using this theorem only you are going to check whether the given language is regular or not, right? Here see here first how you are going to prove that language is regular or not by using the pumping lemma. Here first we have to assume that L is a regular language. First we have to assume that L is a regular language. First we are assuming that L is a regular language, though, so pumping lemma should hold for L. So whenever we are going to pumping any alphabet into the particular string, that particular string must belongs to L only, that particular string must belongs to L. Use the pumping lemma, we obtain the contradiction, select W in such that W is always greater than or equals to N, select Y should always greater than or equals to N, select X such that X Y always less than or equals to N. We have to use these three properties, assign the remaining string into Z, then select k such that resulting string L is not in L, hence L is not regular, By using the pumping lemma we are checking that the language is regular or not, right? Here we have to follow these rules, and we have to follow these rules. Y greater than 0, x y mod of x y less than or equals to n, for all k greater than or equals to 0, x y power k z for all z. See here. For example, here prove the following languages are not regular. L1 equals to 0 power n, 1 power m, m greater than or equals to 0. Here these four examples are there. Here in this class I am going to explain only one example, 0 power m and 1 power m, where m greater than or equals to 0. Here I am going to explain this thing only. Here remember remaining problems, you have to understand the remaining problems, I will give the notes, right? First 0 power n and 1 power n here, then m greater than or equals to 0. See here, instead of m I am going to take n here, n greater than or equals to 0. So already n greater than or equals to 0, my first property is satisfying the first property. Second one is choose w equals to 0 power n, 1 power n, where w mod of w equivalent of 2 n greater than or equals to n. So see here 0 n terms, 1 also n terms, right? Now given a partition w equals to x y z, where x y less than or equals to n and y greater than 0, y should be greater than 0 or else y should be greater than or equals to 1. So greater than or equals to 1, it indicates y greater than 0. Note that this string x y consisting of only zeros and zeros, otherwise mod x y greater than n, For example, let y equals to 0 power t, so x equals to 0 power n minus t and z equals to 1 power n. Here strings x and y consisting of only zeros only. Otherwise, here we are going to otherwise mod xy greater than n, otherwise mod xy greater than n. So, here I am going to assuming that y equals to 0 power t. So, whenever y equals to 0 power t, x becomes the 0 power n minus t, x becomes the 0 power n minus t, and z is, my z value is 1 power n. Now, here choose k equals to 0, x power y power 0, x z. So, if I am going to take k equals to 0, then my string belongs to x z, x y power 0 z, that is x z. X z is not belongs to L, x z is not belongs to L. That is the reason here 0 power n and 1 power n is not a regular language. By using the pumping lemma, we are going to check whether the language is regular or not. Here most of the languages are going to be not regular by using this pumping lemma. With this, second unit is completed. In the second next class, I am going to continue with the third unit. Right? Thank you.